Hey, this is Benji with VP Workshop. This video is going to be an introduction to Blender Toolkit. In future videos, I will cover the workflow of actually building a table, as well as some tips and possible hurdles or maybe script errors you might encounter when using the toolkit. Much of what I'm describing is available on the GitHub README page for VPX Lightmapper. Um, but many of the terms described there are a little out of context if you're kind of new to this, and it may be difficult to understand unless you already have an intricate knowledge of game rendering and programming. Although I really commend Niwek for everything he's done in developing this, and even it takes a long time to write a README. Um, and if you poke around, maybe Google some terms, you could probably piece together what's going on. But I'm going to try to approach it from the way that I've learned Toolkit and explain it in a way that's easy for me to understand. VLM or Visual Lightmapper is a Blender add-on. It allows you to import a VPX table, set up new material and lights in Blender, and render these back out to the VPX file in a standardized way, which allows all these new light images to be animated using VPX 10.8's various new features. In the past, there have been many tables that use high quality rendered images from various 3D applications and import them back into VPX. And there was also various advanced scripting techniques used to exchange the lights on version of a render from the lights off version and sync this all up with the VPX lights and the outputted signals from the ROM from VPIM MAME and make all this look beautiful. We called these variations of these former methods like texture swapping or image swapping. Most of G5K's Adams family was rendered with V-Ray and Maya, and this shows too because it's just gorgeous to look at. So let me explain this the best as I understand it, and I may have things turned around, but hopefully this will make sense. Basically, what's going on here is that there's an original mesh for the objects, which have rendered images mapped on them that correspond to the lights on state of the table. Usually just the most noticeable lights were set up this way. Um, like there'll be special meshes made for the when the flashes are on, when the GI's on, maybe any special inserts. So there's a mesh for the original mesh for the lights on state, and then there's another mesh for the lights off state of these objects. And this mesh has its visibility parameter in VPX animated in the script in time with the animation of the light from the ROM. So you get this mesh turning on and off with the ROM over the top of the original mesh. And that gives you some fading effect. So to show you some of this binary swapping, I've loaded Adam's family into Blender. So I've imported G5K's addon family into Blender with Toolkit, and let's use the Packard car object on the table to see this binary texture swapping. So, so there's GI on, GI off, and GI on with the lights on. So I'm manually swapping these, and it's pretty binary. And when this is done in VPX, it's also pretty binary, right? It's not very smooth, and the lighting, when it does fade, it fades with opacity, and the light isn't properly blended. So imagine manually rendering out all of these different lighting states for all the different objects on the table and trying to hook them up via scripting, right? So you'd need a scripting master at your even now we need scripting masters to hook some things up. But this table was scripted, I believe, by DJ Robx, and they really paid a lot of attention to detail. Like they decided we really want to have the lights on this polar bear. We really want to have the lights blinking on the car, and just to create that is a whole other render that has to be hooked up in the script. Also, even on Adam's family, the reflections of the inserts aren't taken into account. Um, there would be reflections on this metal ramp here from these insert lights, and you can see the inserts just being illuminated via standard VPX lighting. So there's no 3D import from uh, from Maya for the inserts, which Toolkit allows you uh, to do all the inserts so that everything has been 3D rendered and baked, and you get uh, reflections and baked lighting for every light on the table. So here's a work in progress I've been building with Toolkit. Police Force, the Williams table from 1989, I believe. But Toolkit has automatically rendered out all the lighting scenarios across the table, taking advantage of the latest VPX features, which allows for advanced blending of HDR images. So you get tons of interacting reflections and overlapping blended lighting effects, all by just building a version of the table in Blender with all the lights on, and the Toolkit takes care of the rest. It's so cool to look at the table once everything's been processed by Toolkit, because you've never, working with it in Blender, you've seen each light on and off, but you've never seen it all working together with the table ROM. Um, so that's kind of, I guess it's image texture swapping 3.0 is what Toolkit allows us to do. So before we get into the different steps that Toolkit goes through to process a batch, we need to talk about texture baking and define some terms. We need to define the two different ways that Toolkit and Blender render textures. So if we look at the Blender documentation, there are two ways that baking is described. We have this view from, and these terms are referring to the source of the reflection ray directions. Above surface, cast rays from above the surface, and that's actually the surface all the way around the object. Or active camera, use the active camera's position to cast rays. For our intents and purposes, we're going to call these surface baking and camera baking. Camera baking is the default mode used by Toolkit for all objects, and surface baking can be assigned on an individual basis. So what's the difference between the two? Think of camera baking as rendering an image based on what the camera sees from a top-down perspective. So the camera's here, right? Camera's here, table's down there, and it's what the camera sees from this angle. Anything the camera sees from this top-down view is rendered all the way around the geometry. So think of camera baking used for the plastics on a table, plastics are usually horizontal planes with a very thin thickness. And whatever texture ends up being wrapped around those very thin sides is not very visible, right? So let's look at this Colombian cocaine cartel plastic in Police Force, and you can see the top is undistorted, right? But the thin sides, you can almost see how this texture is kind of stretched down the side. So you can imagine that if the texture were being shot out of the camera, it hits this flat plane, and then it kind of spills over the edge and stretches down. And you can see it spilling over the edge and stretching down the rubbers. You can see some of the stretching on these posts here. Where else can you see it? You can see it on the side walls over here, right? But you kind of have to go out of your way. Like, you have to really kind of get in here in VR and look around and point it out. And all those were baked using camera baking. Now think of surface baking as baking from the object's perspective. It's an omnidirectional bake. It bakes taking into account the object as it looks from all angles rather than just from the camera's perspective. But the downside is that this takes up much more texture space. I mean, and that makes sense, right? Because if for camera baking, all you need is the UV data that the camera sees from its perspective, then all you need is basically one plane of UVs that happen to be facing the camera, and the rest, whatever's around the sides or underneath, that just spills over and gets stretched down and wrapped around the object. Um, but for surface baking, you need the UVs that are facing all directions. And in order for this to look right, you have to manually unwrap those UVs and lay them all out. So when the surface baking, uh, so that the surface baking can be performed accurately, and this naturally takes up much more texture space. So while it's not ideal for the texture to be stretching down the sides of the plastics or down the sides of certain walls, it also takes a lot more work and space in the file size and render time to unwrap each object's UVs and to bake all the lighting variations um, that maintain those unwrapped UVs. Um, so if we look at some renders rendered with each method, this is an example of how the plastics and other objects are rendered using camera baking. And notice how these plastic renders are able to have a lot of different objects rendered from the camera point of view, all in the same image. Okay, whereas if we look at the police car, um, this is done using surface baking, and there's something like 29 images for all the different lighting scenarios of the police car. You have to have one image with for every lighting state. And these red ones are obviously the police car when the flasher is going off. But the benefit is that looking at the police car now here in the live editor, you can see there's no distortion. I mean, maybe I could probably improve some of the UV unwrapping on the windows. There's like a little, some sort of distortion in there. But for the most part, this texture wrapped around here is the result of many different photos of this particular object taken, and then Flubber worked on this model here. And you can see the textures are not stretching down the sides as they are with the, like for example, the wood, what is that called? The wood side rail over here. Other examples of baked objects on this table are the flasher domes, right? There's no distortion there. The bumper caps, and then usually plastics are flat and horizontal, and they're good candidates for the default camera baking. But these plastics here, right? The firing range, this jackpot flasher, and the city jail have these these horizontal portions to them. And so if we projected them from the camera's perspective, there would be some large, obvious distortion on them. Right, so here's the jail renders, cycling through them for all the different lighting states on the table. And you see these really dark ones are probably just picking up a couple inserts or some GI lights that are far away. Right, and then there's the render for each of the lighting states of the villains here, the criminals. Right, and so in VPX, these images can be stacked on top of each other. So you could have the lone shark lit plus the drag rat lit, and they'll be added on top of each other. And that's one of the benefits of the new VPX features, is that the ability to add these rendered lights on top of one another in a way that looks realistic, right? They're HDR images rendered on top of each other. These are actually EXRs, so they contain a lot of light data. And when they're all packed together, they're packed together in giant EXR packed texture maps. So now that we understand the different kinds of rendered images that Toolkit generates, we can talk about the kind of geometry that it generates. This kind of geometry is called light maps and bake maps. Here I have every light turned off, including the environment lighting, except for flasher 125, which is the lower left flasher on this table. In this project file, it's a past version of Police Force that I've already run the Toolkit batch on. And at the end of the batch process, Toolkit created a collection called VLM.result. And in this collection is all the light maps and bake maps of the table. So I've got all the other objects disabled here except what is inside VLM.result. And if we look at the object names in there, we can see that they are named according to whether they are a light map or a bake map. And we can also see in their names the name of either the light they are associated with for light maps or the object they are associated with for bake maps. So looking through the collection, most of these are light maps. So see .bm, there's a bake map, and then it's like a bunch of light map. Oh, there's a bake map there, .bm, light map. So most of them are light maps, and then there's bake maps scattered in there. So if we do a search for all the objects labeled as bake map, let's see what happens. So I'm going to search for BM, okay, and then I'm going to select all the objects, and then I'm going to solo them, right? Okay, so these are, oh boy, which one? How's even didn't even tell. So notice nothing's changing, right? Okay, that's interesting. So let's do the same thing for light map. Search for everything with the light map. LM, enter. All right, there's gonna be a lot more of those. I'm gonna have to click up here, all the way down, click on the bottom, and then solo those. Okay, that's interesting. So look at how everything's kind of chopped up. Okay, so when we soloed the bake maps, it looked like just the table looks in normal shader view. When we look at the light maps, it looks the same, except the geometry is sliced up all weird. If we look at the different objects labeled as bake map, we can see that the bake maps constitute all the geometry of the table. But if we look at everything labeled as a light map, we see the same thing, but all the geometry is sliced up. So let's do a search for Flasher 125. Remember, we got Flasher 125, and here's all the areas that's lighting up. Let's search for that in here and see what we get. So we'll go F125. Okay. And then we will select all those. Okay. Interesting, right? So we have some chunks of the ramp here. We have part of the county jail up here, it looks like. Or just the playfield portion of it, actually, not even the county jail. We definitely have all of the flasher dome included in the plastic below it. So let's look at this and then compare it to this. And I think what you'll notice is that all the area that's red is included in this mesh, and kind of all the black areas are cut out, right? Like, it's not perfect, but that's what the light map's doing. Okay, so what we can see is that pretty much anything that doesn't render as black is chopped up and included in this light map mesh. So this is the light map for Flasher 125. So in summary, bake maps are the base meshes of the table. They always stay visible, and they have the default room lighting or environmental lighting applied to them. And light maps are the meshes. They're a kind of shell or a light wrap that gets added over the top of the bake map meshes. The light maps are the meshes that fade on and off over the top of the bake maps and that correspond to the maximum light influence of the inserts, flashers, and GI lights of the table. On the VPX side, once Toolkit finishes exporting the light maps and the bake maps, everything in this VLM result collection gets injected into the VPX table in two different layers. One called VLM.visuals for the bake maps, and one called VLM.lightmaps for the light maps. And so if we go into VPX for police force and we look into this table that's already been exported from Toolkit, we'll see these two layers here, one called VLM visuals, and if we look inside there, we'll see everything in here has underscore BM for bake map, right? And then everything in the light maps layer has underscore LM for light map, right? So putting this all together, we can now discuss what each step of Toolkit does when it processes a table. Remember that before the toolkit batch is actually run, you will have organized all the lights and objects in a way that Toolkit is expecting to see them for processing. For example, uh, with the proper naming and organized into the right collections. That being said, the 5 steps of the toolkit process are groups, renders, meshes, nest maps, and then final export. And during this process, there will be folders generated next, one folder generated next to the Blender project file with 3 folders inside it. So here's here's an old police force export folder. So we have police force local. There's the project file, and then in the project file, there's a couple bake folders for different project files that I've had in here. But we'll just look at this one, and inside of it is 3 folders: renders, object masks, and export. So let's talk about the first operation, the group step. During the group step, Toolkit organizes all the objects that will be camera baked into groups and separated. The group, what objects end up in which group depends on the way they overlap. And so the idea is for all the objects to be baked from the camera and none of them to overlap. And then, and this is a little abstract, but it's important to explain to understand the entire process, during the group step, a bunch of object mask images are generated in the object mask folder, which will be used by Toolkit later to um, cut out all the rendered um, textures from all the rendered images. So it's a way of optimizing, cutting out like a cookie cutter, just where the image is, and then it'll get packed later. Okay, so the next step is the render step, where Toolkit performs all the camera bakes and surface bakes for every light scenario of the whole table and spits all these images, this can be thousands of images, out into the renders folder. It also, before it renders images, it analyzes the maximum light influence for each light, and it excludes any renders which would fall below a threshold which isn't visually necessary, um, or barely visible, or barely has any effect on the table. And this is done to help optimize final performance in VPX. So this step generates tons of images. And you can see for police force, there are almost 2,000 images generated. And before optimization, this amounts to almost 4 gigabytes of images. But after the nest map step, and after all the images have been optimized and packed during that step, the final size of all the images together will be around 100 to 200 megabytes. So that's another cool thing about Toolkit is the insane amount of optimization and consolidation of rendered images that cover the lighting scenarios of the whole table, automatically optimized into an extremely manageable size. Then, let's see, this would be the third step is the meshes step, and this is simply where Toolkit generates the light maps and bake maps for the table, which we already talked about. Fourth step is the nest maps step. And here the object maps that we talked about from the group step, those just black and white images on alpha, these are used, you don't actually see this happening, but if you watching terminal, it'll say creating nest maps. And this step actually can take the longest time because it's very complicated what it's doing. But it's using these masks to cut out all the rendered images from those 2,000 images, to cut out just where the textures are, and taking these cutouts and packing them very tightly into efficient texture images called nest maps. Probably called this because all the renders for the light maps and the bake maps are nested or packed inside of them. So if we go into the exports folder, you will see these crazy, this is an 8K image, right? So if I zoom in, this is 100% zoomed in, right? So if we go into there, you will see the final you will see the final nest map images, and notice that one of them in particular looks a little different from the rest, right? Because these are kind of like warm looking, like, you know, there's a bunch of red for the red flashers. But if you look at this one, right, there's like no lights on. It's on a transparent background. It's just on a PNG. It's not even an EXR. Well, here's the EXR for it. Yeah, so don't forget about this one. But look at this one. Nest Map 0. Um, it contains the rendered images for just the bake maps. And remember that the bake maps are the base geometry of the table, and they have the brightest room state, or the environment lighting, or what you could consider to be the neutral light state of the table, mapped onto them, and that's represented by all the geometry in this image. So here's 100% zoomed in, I think is here, right? And so all this will get mapped onto the bake map geometry of the table. The final step is the export step, and during the export step, Toolkit injects all of the light maps, bake maps, and nest map images back into the VPX file and exports this new appended VPX file. And the nest maps are so efficient that what used to be almost 4 gigabytes of images now becomes like 1 or 200 megabytes, and that'll happen during the nest map stage. And then those smaller images, even though they're 8K, you know, this one's the EXR of it's 38 megabytes, and the WebP version is 23 megabytes. That's just insanely small for how many renders it represents. So that's all the steps. I know I didn't cover all the nuances of what Toolkit does, and more of this is explained on the GitHub README, but hopefully you're tracking with this enough to be able to follow a future video where we'll talk about building a table for Toolkit. And until then, I hope this makes sense and you are feeling more encouraged to dive in and make some of your favorite tables look more awesome in Blender.